Hey everyone, and welcome to this explainer. Have you ever wondered how your computer manages the sheer chaos of data it processes every single second? Like, how does it perfectly remember the exact sequence of your undo clicks, or flawlessly line up documents for the printer without skipping a beat? Well, it all relies on two incredibly elegant fundamental structures. So let's dive right in and uncover the mechanics behind stacks and queues in C++. Here is our roadmap for today. We'll start with 1, the big picture. Then 2, stacks, last in, first out. Next is 3, coding stacks, arrays and lists, followed by 4, queues, first in, first out. After that, we hit 5, coding queues, arrays and lists, and finally 6, picking the right tool. All right, let's jump right into section 1, the big picture. When you look at the entire universe of data structures and algorithms, it's really all about progression. You start with basic arrays and simple sorting, you move on to linked lists, which we've already covered, and now, boom, we arrive at stacks and queues. These are your absolute essential stepping stones. You practically have to master these linear structures before you can even think about tackling complex, nonlinear topics like trees and graphs. They are for sure the backbone of efficient problem solving. Moving right along to section 2, stacks. Last in, first out. The core concept here is LIFO, last in, first out. Picture a stack of plates at a buffet. When the kitchen brings out a new, clean plate, they put it on the very top of the stack, right? And when you go to grab a plate, you don't pull from the bottom, you take one right off the top. The last plate added is the very first one taken. Your computer uses this exact same logic for things like the undo button. The last action you took is the first one undone. In practice, when we use what's called the push operation, we drop a new element, like the number 1, 2, or 3, straight onto the top of the stack. But when it's time to actually remove an item, we call the pop operation, which just pulls that most recent element right back off the top. Oh, and we can also use an operation called peek if we just want to look at that top item without actually removing it. Super handy. So, why does this matter? Well, stacks offer massive advantages in real-world programming. Because of their LIFO nature, they are literally the perfect tool for reversing the order of elements. They seamlessly manage function calls behind the scenes, so your computer always remembers where to return. They form the beating heart of depth-first search algorithms, and yeah, they are the secret sauce behind every single undo and redo feature you've ever relied on. Okay, section 3, coding stacks, arrays and lists. Let's look under the hood. When an array allocates memory for a stack in C++, we set a fixed capacity upfront, say space for exactly 10 elements. We then use a special integer variable called top. When the stack is completely empty, top is set to -1. As we add elements, top simply moves up to track the index of the highest occupied space in that continuous block of memory. The crucial point here is the logic behind pushing an item into this array. It takes 3 precise steps. First, we absolutely must check if the stack is full. If top equals our maximum capacity -1, we throw a stack overflow error, which is a term you might be pretty familiar with. If there's room, step 2 is to increment our top index. Finally, step 3, we assign our new value to that brand new top slot in the array. But what if you hate being tied down to a fixed capacity? That's where linked lists come in. Here, the stack isn't one rigid block. Instead, it's a chain of totally independent nodes scattered in memory. Our top variable is no longer a simple index. It's a pointer holding the specific memory address of the newest node. To push a new item, you just create a node, point its next arrow to the current top, and then declare your new node as the new top. Boom, no more stack overflow limits. Comparing their memory layouts makes it super clear. With the array, it's a clean, contiguous block. It's rigid, sure, but incredibly fast because the computer knows exactly where every single index is. The linked list, though, is dynamic and totally flexible, chaining nodes together via pointers. It only uses exactly as much memory as it needs for its data, although it does require slightly more space per item just to store those pointer addresses. Pivoting now to section 4, queues, first in, first out. If stacks are LIFO, queues are FIFO, first in, first out. Honestly, this is incredibly intuitive because it works exactly like waiting in line at a coffee shop. The first person to get in line is the first person to get their coffee and leave. The last element added to a queue, well, it just has to wait until everyone ahead of it has been processed and removed. Instead of push and pop, queues use operations called enqueue and dequeue. When you enqueue, you're joining the back of the line. When the system is ready to process an item, it calls dequeue.
taking the element exclusively from the very front of the line. It's orderly, it's completely fair, and it perfectly maintains the exact sequence of arrival.
So why choose a queue? Queues are your best friend anytime you absolutely must process elements in the exact order they arrived. Think about task scheduling on your computer's processor or sending print jobs to a busy office printer. They also drive breadth-first search algorithms and handle critical resource management where requests just have to be dealt with systematically.
All right, Section 5, Coding Queues, Arrays, and Lists. Unlike a stack, which only needs one tracker, an array queue actually needs two, a front pointer and a rear pointer. When we add or enqueue items, that rear pointer moves forward. When we remove or dequeue items, the front pointer moves forward to the next person in line. And to avoid wasting empty space at the front of the array once items are removed, C++ developers often use a little math trick with the modulo operator to make the array behave in a circular way, wrapping the rear back to the beginning if there's space. Pretty clever.
Implementing a queue with a linked list also uses those front and rear pointers. When we enqueue numbers, say 25, 50, and 75, we are dynamically creating new nodes and hooking them onto the rear of the chain. When it's time to dequeue, we simply look at the front pointer, capture its data, shift the front pointer to the next node in line, and delete the old node right out of memory. It is a wonderfully fluid system.
And finally, Section 6, Picking the right tool. At the end of the day, whether you are building a stack or a queue, you have to choose your underlying structure. Arrays give you brilliant simplicity and constant time speed, but you are completely trapped by a fixed size. If you guess wrong, you hit that overflow error. Linked lists give you absolute flexibility. No need to specify a size up front. But they're slightly more complex to code, and they definitely eat up extra memory to store those pointer addresses. So here's your cheat sheet. If you know exactly how much data you'll be handling, go with the array implementation for its straightforward, constant time speed. But if your data is unpredictable and you really need dynamic scaling, the linked list is absolutely the way to go. We've spent this explainer talking about normal queues, but what happens when some tasks are simply more important than others? I'm going to leave you with this challenge. How would you differentiate a priority queue or a circular queue from what we just learned today? Think about how you would actually implement those advanced structures in C++ and where they might be applied out in the real world. Dive into the code, test it out, and keep building. Thanks so much for joining me in this explainer, and I'll catch you next time.